In this chapter, we're going to discuss a special property of molecules called aromaticity. Aromaticity was first discovered in the molecule benzene. So we're going to start by looking at the molecule benzene and the special properties that aromaticity gives it. So benzene was discovered in 1825 by a scientist named Michael Faraday, who you may have heard of if you studied physics for Faraday's law. At that time, when a substance was discovered, chemists would first determine its empirical formula in order to try to identify it by formula. Benzene, however, had a very interesting empirical formula. The empirical formula of benzene is CH. It wasn't until later, when experiments allowed determination of the actual mass of benzene, that the molecular formula of C6H6 was determined. With so few hydrogens in the structure, in the formula, it was a matter of great debate what the structure of benzene would actually be. It wasn't until 1865 that a scientist named Kekulé proposed this structure for benzene. This is called the Kekulé structure of benzene, a six-membered ring with alternating double and single bonds around the ring. Now, this structure was actually somewhat controversial, although there was at the time very good evidence for it. The first problem with this structure that we see is that we know that double bonds are shorter than single bonds. And so while I've drawn it as a reasonably good hexagon here with all equal sides, in reality, this structure implies something more like this, although the relative lengths of the two sides, the double bond and single bond sides, has been exaggerated. But it would have shorter sides on the double bond, longer on the single bonds. The problem with this then is that certain isomers, in particular, for example, if we put two chlorines onto the benzene ring and it had this structure, there would be two different isomers of 1,2-dichloro, of the ring with two chlorines adjacent, because there would be one constitutional isomer where the two chlorines were each on a carbon of the same double bond, but there would also be a constitutional isomer where the two chlorines were on a carbon of two different double bonds. Two different dichlorobenzene constitutional isomers have never been observed. So therefore, Kekulé modified his structure by proposing that perhaps the double bonds were equilibrating rapidly around the ring, sort of shifting to the single bond positions, making them double bonds, and that this equilibrium was so rapid that effectively the two different constitutional isomers were appearing to us as being the same. We now know that this is also incorrect, but interestingly enough, this looks kind of like resonance that was incorporated later into the bonding theory. When the Lewis rules came out, it became a problem that there were certain molecules that could have two distinct constitutional isomeric Lewis structures, but for which only one actual example of the molecule had ever been observed. And so we it was proposed the resonance theory, where each of the structures was considered to describe some aspect of the molecule, but that the real molecule was a hybrid that sort of mixed all of the structures. Well, interestingly enough, if you make a hybrid of benzene by assuming that everywhere that there is a double bond part of the time and then a single bond the other part of the time, you get sort of a partial double bond. What you end up with is a ring of double bonds going all the way around 6 carbons. This would be sort of our picture of the hybrid. Note that this does violate the Lewis structure rules. So there is no official way in Lewis structures to draw a hybrid. However, what we would say is that we had delocalized bonds. In chapter 15, we talked about that what delocalized bonds represent then is or are pi bonds that extend simultaneously over 3 or more carbons. And so our modern pi molecular orbital view of benzene is that each carbon of the benzene has a p orbital that contributes to a pi bond, and the pi bond is one pi bond that goes all the way around the ring, delocalized around the ring. In other words, it's sort of a donut-shaped cloud of electrons, simultaneously half above and half below the 6 carbons of the ring. This was given the special name of a cyclic pi system, a pi system that is delocalized all the way around a ring. Now, benzene's formula was not its only unique and interesting property. Once scientists had sort of decided upon a structure for benzene that had double bonds, they expected it to do normal alkene-like reactions. So an example of a quote-unquote normal alkene reaction is this. Take an alkene double bond, react it with bromine, the double bond disappears, and one atom of bromine is attached to each of the carbons of the former double bond. We call this halogen addition, in this case bromine addition. It was discovered experimentally that benzene does not do this addition reaction. It's unreactive under these conditions. So if we take benzene and we mix it with Br2, we essentially get no reaction. However, it was also discovered that if we tried to use force to get it to react, in this case by mixing it with a Lewis acid, iron tribromide, that instead of getting addition, what we got was substitution. So the bromine was reacting with the carbons of the ring, but it was replacing one of the hydrogens. It wasn't adding to the double bond. The double bonds stayed unaffected. So this is one unusual property of benzene. Another unusual property of benzene is its unusual stability. Now, let me sort of walk you through the experiment that kind of gives us a really good idea of what this unusual stability is. So we've seen this experiment before where we take a double bond and we treat it with hydrogen and palladium, platinum, or nickel in order to add hydrogen, hydrogenate the double bond. And we also saw that this reaction going from having a double bond to having it completely saturated was an exothermic reaction and could be conducted in such a way as to measure the amount of heat given off during the reaction. Finally, we saw that because heat was given off during the reaction, our product had a lower potential energy than our reactant. And so the larger the amount of heat given off, the higher we expect our reactant to be relative to the product. And therefore, it's sort of a measure of how stable is that reaction. Higher potential energy means less stable. In chapter 15, we also looked at what would happen if we had more than one double bond in a ring or in a molecule. And we saw that if the double bonds were not adjacent to each other, then each double bond would react independently and would give off basically its own proper amount of potential energy, and the potential energies would then be additive. So for example, here we have a cis disubstituted alkene. The heat of hydrogenation is approximately 28.5. And what we see is when we put the second double bond in but have it be isolated from the first, the heat of hydrogenation is just a little bit more than double 28.6. However, if we moved one of these double bonds so that now the double bonds were adjacent, or in our terminology, conjugated, we saw that conjugation increased stability. In other words, it lowered the potential energy. And so the equivalent conjugated diene, when it was hydrogenated, it had a heat of hydrogenation about 1.8 kilocalories lower than the isolated diene. And in that case, we would say that this was more stable by about 1.8 kilocalories. So continuing that line of thought then, it was assumed that if we then put a third double bond in there, that would add, approximately another 28 to 30 kilocalories. And so we would predict a heat of hydrogenation of benzene, if we fully hydrogenated it, to be about negative 85.8. So here's 1, here's 2, here's 3. In fact, actually, it was found that when you hydrogenated benzene, the heat of hydrogenation was significantly lower than 85.8. It was only 49.8. If we put that on the graph, then we can see that benzene is actually more stable, has a lower amount of potential energy than the dienes, the two molecules that have two double bonds in them, which is really surprising because we at least assume that every double bond adds potential energy. So it has an exceptional and totally unexpected amount of stability. In fact, this stability is often called the resonance energy of benzene, and it's estimated at about 36 kilocalories per mole. We don't really know because we've never been able to make a molecule like this and hydrogenate it and get what its actual heat of hydrogenation would be without the benzene aromaticity effect.